Hello, everyone, and welcome to our webinar. My name is Johanna Manso, and I am the Logistics and Events Manager for Internet System Consortium, and I am your host for today. The title of our presentation today is Anycast, and our presenter for today is Leo Bregnell, Senior Architect, System Architect, sorry. Several quick pointers. This webinar will run for approximately 1 hour. All webinar participants are automatically muted upon entry. This webinar is being recorded and will be available on our website within 3 business days. If you have questions, please enter them into the WebEx Q&A tab for us to answer it. Now, without further delay, I present to you Leo. Go ahead, Leo.
Hello, everyone, and welcome to the webinar here. While I'm going over the agenda, I'm going to open a poll here that you should see in WebEx. If you can all take a quick look at that question and give us an idea of your background, that would really help. What we're going to do today is we're going to define Anycast. We'll then look at some of the use cases for Anycast. We'll explore the impact on commonly used Internet protocols. We'll then take a closer look at Anycast and DNS, because we're sure many of our participants are very interested in DNS. And we'll then also share some of ISC's operational experience with Anycast with some of the services we've deployed. There'll be a Q&A at the end. However, if you have questions at any time during the presentation, please enter them in the Q&A tab. We'll take them as we go, as we can fit them in. And if we have to save them for the end of the section or the end of the presentation, we'll do that as well. So let's get started here. The first thing that we need to do is we need to define Anycast, so we're all talking about the same thing. And Anycast is a method of using the same IP address on multiple servers. And what that really means is that Anycast is fundamentally a routing scheme. You'll find that Anycast is more about how you route IP addresses on the network to reach a server than it is about the actual configuration on a server. There's no, for instance, configuration in bind specific to Anycast. Now, what is a routing scheme? This is something people often don't think about in these terms. So what I'm going to do is I'm going to kind of set a baseline here where we have one client, the red dot on the left, and a bunch of yellow servers that are out on the network. There are several ways that the client can contact those servers. The most common that people are used to is unicast. The single client makes a connection to a single server and gets served some amount of data. Another one that people are very familiar about, particularly at the LAN level, is broadcast. The one client can contact all of the servers at the same time. A refinement of broadcast is multicast, and that's where the one client connects to some subset of the servers. And lastly, we have Anycast. Anycast is a scheme where there are multiple servers that can service that client, but the client only connects to one of those servers at any particular time. So what are the properties of Anycast? Well, each packet sent to an Anycasted IP address might reach a different server. Packets are routed to the IP address with the best network metric. Again, this is a routing scheme, and so the network controls where the packets go. Now, the best network metric could indicate the nearest server, and this is often what people think about in their mind when they think about Anycast, but it doesn't have to be the nearest server or the fastest server. Network metrics can be set on many other factors such as bandwidth, the monetary cost of the link, load, reliability, or even criteria such as your favorite ISP or anything else that people might use to set network metrics. One of the things that this means is that servers with an Anycast address must generally also have a unicast IP address. If you think about trying to manage your Anycast server using SSH or SNMP or any of the protocols you might use, if you went to that Anycast address, you'd only get one of the servers in your cluster. So to manage all of the individual servers, they generally also need a unicast IP address that you can use for those management functions, so you can contact all of the servers. Before we jump into the use cases, just another reminder that if there are any questions along as you go, feel free to jot them in the Q&A tab, and we will get to them as we can. See, a couple people haven't answered the poll yet, so please take a look at that if you haven't. Let's talk a little bit about the use cases. Local Anycast is the first thing I'm going to go through, and that's not a well-known industry name or anything like that. That's just a name I've given it here for this presentation. And I'm using that to describe when all of the Anycast servers are located on the same subnet. So I've drawn a picture here with a router and a subnet, along with 4 servers on it. And what we're showing in the router is the Anycast address is routed to all 4 different servers. And generally, the way this is done is with flow-based, equal-cost, multipath routing. We'll talk a little bit later about some of the other things that can happen in a router, but for now, just remember that the packets coming into that Anycast router are distributed amongst all 4 servers. Now, how did those routes get into the router? Well, they can get in there using any of the standard ways you would get a route into a router. These could be statically configured routes. They could be routes learned by a dynamic routing protocol such as OSPF or BGP. And in fact, a dynamic routing protocol is often used on the servers so that if one of the servers fails, the route is automatically removed from the router. A common option for doing this is to use Quagga on the servers. And in fact, ISC is involved with Quagga development. We have the open source routing forum, which is working on Quagga code improvement and feature addition. So we use Quagga on the servers for this purpose a lot. Another interesting option is active service probing from the router. Cisco has a feature they call IP SLA, and these are active probes the router can issue to see if a service is up or there's a particular latency on a link or a number of criteria. And those can be used to add and remove static routes from the router. But the key here to remember is that any of the methods that get those routes into the router are perfectly valid in an Anycast deployment. With local Anycast, being that all the servers are behind a single router and on a single subnet, one of the great things that happens is that only one route is going to leave this router. The router is going to say that that Anycast network is routed to it, and then it will fan it out to the 4 servers. And as you'll see later, this sometimes can mitigate some of the other problems that might occur with Anycast routing, and so this can be a very safe way to deploy Anycast. The other form of Anycast is what I'm going to call global Anycast, and this is a method of distributing load across multiple locations. This is typically used to provide redundancy or to reduce latency in networks that span large geographies. In this case, we've got 3 servers on the right and a client on the left, and there's some set of routers forming a network in the middle. You can think of this picture as your typical enterprise or ISP network. Now, also, we can alter the picture just slightly, and we can think of this as a collection of internet networks. This is equally valid. So instead of each of those being a router, they could each be a separate ISP with various peering and transit relationships, and those servers could be located on different ISP networks. It's the exact same concept, it's just scaled up to the larger network. We can also combine this global Anycast picture with the previous local Anycast picture by using local redundancy at each site. And this sort of forms the complete set of how you can deploy Anycast depending on what environment you're looking to deploy it in. So what are the most popular things to Anycast? Well, by far, DNS is the most popular thing that people Anycast, and recursive servers are actually the most popular out of the DNS servers. Pretty much every ISP on the planet has Anycasted their recursive servers. The primary reasons for this is that the recursive servers are generally configured by an IP address on the client. This makes DNS kind of unique compared to other services where DNS can actually be used as a level of indirection if the servers need to move or be re-IP'd or whatever. With recursive servers, that simply can't happen. You actually hand the IP address to the client. So by giving them an Anycasted IP address, it provides the ISP the ability to take servers out of service for maintenance, move them around, and so on. Latency is also very important. Users are waiting for their queries to be answered, so getting the servers closer to the users is a very good thing. And many of the larger ISPs need to distribute load across multiple devices, and this is a very cheap, easy, and reliable way to do that. Authoritative DNS would be the second most popular, and it's done for almost all the same reasons as recursive servers, with some additions. The biggest addition is that there's a limited number of IP addresses that can be returned in a single DNS packet. This has certainly been run into at the root zone and with some of the other TLD zones. It's less common with enterprise zones, but can be an issue in some deployments. And Anycast is a way to get more servers serving the data without having to list more IP addresses. All the other reasons still apply. Latency to the server is still important. Redundancy is a large concern. And certainly larger TLDs need to distribute the load across multiple devices. NTP is actually fairly commonly anycasted by ISPs, but this is often completely transparent to the user. Many ISPs deploy CPE equipment that requires configuring NTP by IP address to keep accurate logs, not by name. And so they end up anycasting the NTP servers. This has a little bit of implications due to the way NTP works, but if you consider NTP being anycasted the same way recursive servers will in the diagrams I'm going to show you coming up, you'll see how this can work pretty reliably. The last one I'll talk about more later with some of the secret sauce that people use, but we'll see that it's generally not advised to host your web server on an anycasted IP address, and so people will use an HTTP redirect server on the anycasted IP address. And the idea here is to provide a short-lived, quick connection that can redirect the user to the actual web server they should be talking to. And I'll give an example of this later with some of our advanced configuration. I'm going to pause here for just a moment again. A reminder that if you have any questions during this presentation, you can pop them into the Q&A tab. And I don't see any questions there, so we're just going to keep on rolling along. Now, Anycast does have some protocol-level implications. Fortunately, they're not too hard to understand. We're going to start with ICMP. And the good news is that the bread and butter troubleshooting tools that we all use, ping and traceroute, continue to work just fine. Now, traceroute will show some sort of odd results if there is network instability going on while you use the traceroute command, because the packets will be rerouted to other servers in the middle of the connection. But generally speaking, if you want to see if the Anycast IP address is up, you can ping it, you can traceroute to it to see where you're going. They work just fine. The LAN options are a bit problematic. These options all happen on the local network and are a problem when there is more than one Anycast server on the local LAN. So this is the local Anycast situation. And basically it's pretty obvious. If a box issues an address mask request from an Anycasted address, the reply doesn't know where to go, which one of the boxes on the local LAN. But the good news is here, most of these LAN options simply aren't needed. Most people are already in the habit of disabling redirect messages. Address mask request replies are not needed if you configure your boxes with IP address and mask properly. And so my advice is to simply avoid all of these LAN options by fully configuring your devices. The most interesting thing about ICMP, though, is the transmission failure messages. And there's an awful lot of transmission failure messages, but they all basically have the same properties. And the important thing about these is that an intermediate router generates these in response to some condition on the network and sends those back to the source. And with Anycast and the way Anycast is routed, this can be a problem. So what I'm going to do is I'm going to show you an example, and I'm going to use a source quench message as my example. But the example would work just as well with any of these other messages. So what we have here is a client on the left side, a couple of ISPs that serve that client, and on the right side, we've got a couple of Anycast servers. What's going to happen here is the client is going to send a query that's going to be routed to one of the Anycast servers. And it's going to respond and use its own routing to get back to the client. In this case, we show it going to the other ISP. That ISP is going to generate one of these ICMP transmission failure messages. In this case, I'm showing a source quench in response to congestion. It's going to send that back to the source address of the packet, which is the Anycast address. When that goes back, it gets routed to its nearest Anycast server based on the network metrics. In this case, it goes to the top server. And this is where we have a problem. That message has now been delivered to a server that had nothing to do with the original connection. The result is that the top server is going to discard that ICMP packet because it knows nothing about the connection, while the bottom server will never receive the notification for the connection that's actually active on it. So operationally, what does this really mean? Well, the case that is the most problem is losing the ICMP packet too big message because it breaks path MTU discovery. Packets from an Anycast host basically should never be sent with the don't fragment bit set to generate these messages. They simply go back to the wrong Anycast server, and the bigger your cluster, the more likely they'll go back to the wrong server. Now, there's a couple of ways to work around this problem, and unfortunately, it's a little different in IPv4 and IPv6. In IPv4, if the DF bit isn't set, a router can fragment a packet midstream and send the two fragments on to the destination, and this works perfectly well. The other option is for the server to send with the minimum MTU, and in IPv4, that's only 576 bytes. That's a rather small MTU, and that generally is not very good for performance. So usually in IPv4, you simply have to accept that some packets will be fragmented by intermediate routers. In IPv6, things have changed a little bit. Intermediate routers are not allowed to fragment packets. They simply return an ICMP packet too big anytime a packet's too large to go down the link, and then drop the packet. So the result is, in IPv6, the only safe thing to do is to send all packets with the minimum MTU of 1,280 bytes that's guaranteed to work on all links. The other thing to watch out for because of this problem is that lost messages prevent the orderly teardown of connections. If you think back to the diagram we just went through, the server with the connection never received that ICMP message. For messages that tear down a connection, like administratively prohibited or other messages, that message doesn't make it to the server, and thus the connection lingers around until a timeout is reached using resources on that server. Now let's look at UDP. UDP is a stateless protocol, which is really good for Anycast, and it works particularly well with Anycast when the query is one packet and the response is one-to-many packets, and there's no state between queries, which sounds exactly like DNS, which is why DNS is so popular to Anycast, and while we'll go into DNS in more detail later. If the query is more than one packet, or if you're using a UDP protocol that puts state on top of UDP, then the behavior tends to be exactly the same as TCP, which is a stateful protocol to begin with. So I'm going to go through TCP next, and just keep in mind that a UDP protocol that has state on top of it has the same properties. TCP is a stateful protocol, and what that means is that it only works when the network path is stable. The one client has to talk to one of the Anycast servers for the duration of the connection, so the network has to keep routing packets to the same Anycast server. Now, this is never true in the long term. If you look over weeks or months or years, eventually a router will fail, a link will go down, a user will adjust a metric, and the path will not be stable. But over short periods of time, this is often very true. It's entirely likely that for the duration of this particular WebEx, all of us will use the same path from our clients to the servers that are serving up this presentation. Now, I don't qualify short periods of time because that can vary with the sort of network and service that you're providing. If you, for instance, have networks that are known to be rerouting all the time, wireless mesh networks or something like that, short may be much shorter than if you work in an environment where everything is hardwired and there's a low change, amount of change and so on. So you have to evaluate what short periods of time mean for your environment and your protocols. But again, the key is the sender has to reach the same destination for the duration of the connection. One packet to the wrong device is enough to generate a TCP reset, which will tear down the entire connection. So let's take a little bit of a look at this visually, because that helps some people understand it a little better. We've got a client on the left, a network in the middle, and two Anycast servers on the right. The client is going to send a TCP SYN to a particular Anycast server, and that Anycast server is going to respond like any server would with a SYN ACK packet back to the client. Now in this case, I'm going to show a network that for whatever reason decides to route the next packet in a different direction. So the client now sends an ACK data packet that's routed to the other Anycast server in this picture. That server knows nothing about the connection, so it generates a TCP reset back to the client. Now, when the client gets that, it believes it came from the Anycast IP address, so it tears down the connection completely and stops all communication. So the client gets no service, while at the same time, the server in the upper right that answered the original connection has state for that connection on it that now has to time out because it won't receive any more packets related to that connection. We need to look at the sources of path instability. What causes this problem where packets are routed to the wrong server? The most common cause by far is simply load balancing. Per packet load balancing directs each packet to a different link and possibly to a different server. Per flow load balancing is generally the way to kind of work around that, and it hashes the flows usually based on some set of data in the IP header. A 5-tuple of the source IP, dest IP, source port, dest port, and protocol is by far the most common. However, there are devices that hash on a 3-tuple and devices that have a configurable hash based on all sorts of data in the header. This will create a stable path for many topologies, but it is in fact possible to create some topologies where even a flow-based hash won't be stable to a particular server. Route churn is the second most common cause of path instability, and this is simply things caused by failures like links, routers, or servers going down, but also user configuration. If a network admin gets in and adjusts network metrics or configures a new peering session or any of those sorts of things, it causes a recalculation event, and that could send packets to a different server. The last most common cause is middle boxes. A lot of enterprises and some ISPs employ devices that are sort of route optimizers or WAN optimizers, and they're a kind of load balancer device that looks deeply into packet flows and chooses to reroute them based on a host of criteria. And some of these boxes in certain situations can end up routing different packets to different Anycast servers, not realizing that the servers it's sending packets to are actually Anycasted and it's reaching different devices. So operationally, what does this mean for TCP and other stateful protocols? Well, the location of Anycast servers in the network is very important. It depends entirely on the network topology, configuration, and the sort of devices you're using. So this is a case where the server admins and the network admins need to work very closely together to deploy an Anycast service. However, when properly deployed and all of those things are accounted for, there's a very high success rate for short duration TCP connections. The longer the connection, though, the greater the risk of failure. And again, I'm not going to qualify short and long here, although we'll give some examples with DNS, but you really have to evaluate this for your particular environment. For internet services, things that you're deploying out there on the global internet, it's not just your network. Every network the packet traverses potentially could have these load balancing devices, these middle boxes, and could route packets in different directions. So you have to kind of think about that when you deploy your Anycast server and try to locate them in places that help mitigate the effect of what other networks are doing. But generally, the recommendation would be you should avoid Anycasting TCP services whenever you have a good alternative. there's definitely a higher failure rate for stateful services, and I'll give some numbers in a bit in the examples where we've actually operated some TCP services across the internet. I'm going to take a brief pause here again to take any questions that anybody has. Again, just put them in the Q&A tab. I'm also going to start another poll question at this point. If everyone could take a look at that and answer that, we'd really appreciate it.
Leo, I see a question. So it says, going back a few slides, can you mention any examples of well-known websites using global Anycast for an HTTP redirect service, or is this a rarity?
I have not done much research into exactly how many people are and aren't deploying this. What I can say is that most of the large websites already have very sophisticated global load balancing capabilities with all the tools you might expect used for that, and generally don't use this method because they have better tools that suit their needs. The most common places I have actually seen this deployed is inside of a single network. So for instance, enterprises or ISPs deploying internal service where they have full control over the network and simply want, I would call it a poor man's global load balancing solution. And I'll talk a little bit more about this in one of the later slides. So I'm going to save a little bit more detail for there. So I wouldn't quite call it a rarity, but certainly in terms of major web properties, you know, if you're going to Facebook or eBay, they're not going to be using that technique because they have other and better tools to do so.
Okay. I don't see any more questions. I think we can go ahead and proceed.
Okie dokie. Let me move on here then. So now we're going to go into DNS and Anycast because I'm sure that's a key interest point for most of the people on this call. And DNS is a very good fit for Anycast. Most common queries are a single UDP packet, and they generate 1 to 3 UDP packets of response. And if you think about the things we've talked about, that's a perfect fit for Anycast. Even TCP queries for DNS tend to be extremely short-lived. An awful lot of them are sort of a 6-packet exchange, sometimes an extra data packet, and a few implementations will even let you lose the final FIN packet and the data still goes up the user stack. But, you know, we're talking about usually sub-second TCP sessions from start to finish. So TCP queries are extremely short-lived and thus generally meet the definition of short for all the slides I've used before. The only kind of problematic thing for DNS is zone transfers, because those can obviously be long-lived TCP queries. Now, sites that don't allow zone transfers simply mitigate the issue straight off the top that way. But the length of the transfer depends entirely on zone size. Certainly for a very small zone, the transfer may not take very long. And even for a larger zone, it then kind of depends on the network speed and performance that you can get. But generally speaking, DNS is a very good fit for Anycast. The most common case, as I said earlier, is to deploy end-user resolvers. So I want to take a look at that first, and I've drawn here an ISP network. We've got a backbone at the top, some regional hubs, some points of presence, and then a whole pile of users connected. So this is sort of a standard ISP network architecture. And in this case, I've deployed 4 end-user resolver boxes, 2 each at each of the regional hubs. Now, the ISPs do this for a whole pile of reasons. User queries stay local. They don't have to pay backbone costs to move these queries around, so that's a win. Also, the servers are very close to the user, so it's a very low latency response, which makes the user's perception of the network better. But also, users, again, have to configure resolvers by IP address. So by anycasting it, the ISP has ensured that if any one of these servers fails, the users continue to get service, even to the point where an entire hub could fail, and those users will be rerouted then across the backbone to another site. So this provides high availability and good load distribution for all of the clients. And I would venture all but the most modest ISPs generally have deployed their recursive resolvers in this way because it just makes operations so much easier. So almost everyone in the entire world probably is talking to an Anycasted box and may not even know it. The next most common case is authoritative DNS. And again, lots of the same criteria, but we've kind of got a different picture here. I'm showing an ISP or an enterprise network that reaches across the U.S. And excuse me just a second, WebEx is giving me pop-ups I didn't expect. The authority servers are distributed across the United States here, and the goal here is usually largely to keep local traffic local. So the goal here is to reduce latency to the server, to provide redundancy, and again, Anycast provides a great way here that if a particular site were to fail, the network reroutes and sends the traffic to that Anycasted IP address, which will reach the next best box based on the network metric. A similar case, done for similar reasons, is to look at deploying across multiple ISPs. This goes with the previous picture I showed. But in this case, I'm showing a Asia-centric ISP, a US-centric ISP, and a European one. And again, the idea is to keep traffic local and to increase redundancy, so if any of these fail, it will go over to another server. This is the sort of deployment that F-Root's deployed in, which I'm going to talk about in more detail in just a moment. Now, a couple of advanced ideas here, and this kind of goes back to the HTTP redirect idea as well, but inconsistent content is an interesting idea that a few people have played with. It's part of the secret sauce in a couple of CDNs, depending on which product they're selling folks. But so far, probably you've been thinking about every node in the Anycast cloud having the same data, serving up the same zone. That, in fact, doesn't have to occur. You could load a different zone in each of the Anycast servers. Think about putting a record for www.domainname in your Anycast servers. That A record could point to a different IP address in each of the Anycast servers. And this can work as a poor man's global load balancer, particularly inside of your network, so inside of an ISP or inside of an enterprise. The idea is that you would plop down a web server next to the Anycasted DNS servers. That web server would have a unicast IP address, and the DNS server would return the IP address of the web server that is next to it. Now, this is predicated on the idea that when the user queries a resolver, the resolver is close to the user. The Anycast routing picked the best location. The only problem with this is that most users send their queries to a recursive resolver, and it's that recursive resolver that hits the authority server. So you're picking the web server closest to the recursive resolver and not the user. In some cases, this can lead to very bad behavior, but for most deployments, this is usually good enough. A similar concept that we talked about before is to use the HTTP redirect server, Anycast that service, and simply redirect users to the local web server. And again, you won't see this with the big web properties, but I have seen this inside of enterprises or inside of ISPs for locally deployed stuff. It's a lot cheaper than buying an entire global load balancing solution if all you need is some simple global load balancing. The other thing that I want to point out is that all of the usual routing mechanisms, tricks, and fun stuff can be used to direct traffic in interesting ways. You can use multiple supernets and subnets, and I'll give an example with F-Root. You can use metrics that alter dynamically. I already mentioned Cisco's IPSLA can be used to probe latency or packet loss or service availability and add and remove routes. So when you talk to your routing admins, or if you're the routing admin, all of that configuration sugar that you have to do fancy things can be used in interesting ways to direct Anycast traffic as well. And I'm going to pause here for just a moment again for any questions. I'm also going to open up another poll here. We're curious what kind of Anycast you would deploy if you deployed it. And I'll give folks just a moment here to ask any questions if they have them. Please use the Q&A tab.
I am not seeing any questions, Leo.
All right, I see some people answering the poll, which is awesome. So I'll jump right here into. Oops.
Sorry, one just came in. Let's see. From Bryce, any experience with, I guess, AAA services being Anycast?
No, actually, I don't think I've ever heard of a AAA service being Anycasted. What I can tell you off the top of my head is a service like TACAX would potentially have all of the problems that TCP would have since it runs over TCP. That's a stateful service. But Radius, being a stateless UDP service, off the top of my head, I don't see any reason why that couldn't be successfully Anycasted. That seems like a very good candidate. And seeing any other questions, I think I'll then move on.
I think we can proceed.
Okay. So ISC does operate a number of Anycast services. I'm going to start with our SNS service. This is a relatively new product where we do authoritative hosting for DNS domains. And the way this particular product is configured is that we're present on 3 different ISP networks, Cogent, Hurricane Electric, and Tata Communications. And inside of each one of these ISP networks, we configure Anycast inside of that network only. So we get IP address space from the provider, and we set up a minimum of 3 locations on that provider's network, and then we Anycast inside of their network. But after it leaves that provider, it looks just like a normal unicast route. It's a single route to that provider. And the reason we've done this is that by doing it that way, if we have any routing issues whatsoever, we can go to the provider and they can troubleshoot everything inside of their network. While at the same time, by being on 3 different networks and 3 different locations in each network, including only 3 NS records in a zone, makes the zone available across 9 locations worldwide on 3 different networks. So we've chosen this as sort of the safest way to deploy Anycast because we're doing it only inside of networks that we have a business relationship with, while at the same time getting many of the benefits of deploying worldwide Anycast. And this is a service that, if you're interested, you can sign up for on the ISC website. I've got a picture here showing where the current SNS servers are located worldwide. We are actually interested in deploying some more of those. And what I'm going to do here is I'm actually going to terminate the previous poll just a little bit earlier. And WebEx is making me wait just a moment when I do that. And then I'm going to start a new poll here just to gauge the interest in whether or not people are interested in a service like SNS. It's just a question for us. It won't get you any additional marketing material. But as soon as that opens up, if you could just let us know if your organization would be interested in outsourcing authoritative DNS, we'd like to know that. While you're answering that, I'll move on to F-Root, which is Anycasted differently. F-Root has 3 different levels of Anycast. It is Anycasted on the local LAN. Every place we deploy F-Root, we deploy a minimum of 2 servers, and we do that primarily for redundancy, but also if we need more than 2 for load, we're able to deploy additional servers on that LAN. We deploy local nodes at internet exchange points or occasionally inside of an ISP network, and they announce a /24 in IPv4 and a /48 in IPv6 with the no export BGP community. And this is an example of us using some of the routing configuration ability to use a fairly unique policy. Because of the no export settings, these routes generally will not be visible to end users, and I'll walk through a picture in a moment that shows how this all fits together. We then also have what we call global nodes, and these are larger nodes that contain a significant amount of transit capacity, and they announce a /23 and /47 supernet of the local node prefixes. And these networks should be visible to all end users on the internet. Now, it's a little hard to explain this in words now that I've run through a summary, so let me give you a diagram that will help this make sense. What we have is the global nodes announcing the supernets, and those routes are anycasted sort of the way most people would think of Anycast working, and they reach all of the customer networks across the entire internet. If you look in your routing table, you should see both of those networks. We then have at the local node the more specific subnets, the /24 and /48, and those are announced with no export across the exchange to other ISPs that peer with our local node. So you'll notice on the two IXs I've then distinguished between ASNs that peer with us and ASNs that do not peer with us. So what happens here, once those peerings are up, is that the autonomous systems that peer with our local nodes have both the supernet and the subnet routes in IPv4 and IPv6. And in IP routing, the longer prefix wins. So these ASNs are going to follow the /24 and the /48. Everything below that sort of brown line, though, because of the no export prefix, continues to have just the /23 and the /47 routes. So what happens with traffic? Well, customers of ASNs that peer with F follow their /23 into their provider network, and then the provider follows the more specific route to reach our local node, providing great service, low latency, and all the benefits of the local node. However, customers who are on providers that don't peer with us or on providers that don't even connect to an exchange we're at follow those supernet routes all the way back up to the global nodes and get service that way. So everyone still gets service. We're just able to keep local traffic local. Now, why did we do it this way? Well, we had a very strong desire, particularly early on in the F-Root project, to keep local traffic local. Several of our local nodes were deployed into bandwidth-starved areas. We were behind satellite links or very low, multiple T1s bonded as the only connection into the country. And you didn't want to drag in queries from the more bandwidth-fortunate internet to these bandwidth-starved areas. So we wanted to keep the routes very local. We also wanted to provide an incentive for the local ISPs to peer with the local F-Root instance. By only getting the better service if you peer directly with us, we can establish a relationship, and this means that we know who to contact for troubleshooting, we know who to send information when we turn up additional peering locations to get them connected. We can use that relationship to better the system going forward. We also think that diversity, particularly in the root ecosystem, but this may be an issue for you in your ecosystem, is very important. The root operators use different software on different server hardware, and they use different models. There are anycasted roots, there are unicasted roots, they target different user communities, and it makes it harder to attack the root. It makes it harder for any one problem to bring down multiple servers, and no one else was using this method, so we decided to experiment in this particular direction. You may want to consider what kind of diversity you have in your ecosystem and whether that provides more or less resilience. Now, our configuration does create some confusion. Many ISPs that peer with us initially think that because the route has no export, their customers won't see F-Root. But as you saw in the diagram, this isn't true, but it causes us to have a lot of additional explanations with folks. And I want to mention that to you just because, again, you can use all of the routing knobs at your disposal to direct Anycast traffic, but it may cause some additional problems or confusions, particularly if you're out there playing on the global internet and doing things in a way that people don't expect. Now, with F-Root, zone transfers are not officially supported, but we do allow them. We're one of 4 root servers that allow them. So from our perspective, if you have a long-lived TCP connection doing a zone transfer and it fails, we don't consider that an outage. Now, in practice, the root zone's fairly small, and so generally, zone transfers work just fine. Prior to IPv6 and DNSSEC deployment, TCP queries at the root were extremely rare. Now, this will vary with the zone data that's in your zone. and it depends on the size of the information that has to be returned. If you're DNSSEC signed, there's more data to be returned. If you use large text records, there's more data to be returned, and you're more likely to see a TCP query. Now, I pulled some data. At the root zone, the percentage of TCP queries rounded to 2 decimal places was literally 0.0% before DNSSEC was deployed at the root. And after DNSSEC was deployed and that key material was in there, it went up to 0.2 to 0.4%. So TCP queries are extremely rare in our experience, and again, they're very short-lived. A TCP query for an actual record is, again, just a few packets. It's generally sub-second, and so we see very few problems with TCP queries to the root zone. It's also important to point out that DNS generally handles a non-responsive server in an intelligent fashion. Most DNS implementations track whether servers are responding, and if so, in what response time, and they attempt to direct queries to the fastest responding servers. Now, there are a few exceptions, but this largely means that if a particular server is failing due to network instability or some other issue, the client software will, or the recursive resolver will automatically redirect to other working servers. Now, this means it may not be wise to have 100% of your authority servers in a domain anycasted. Unfortunately, this same property also means that it's very easy to combine Anycast and unicasted servers, as is done in the root zone. Again, F-Root is anycasted along with some others, but there are root servers that are not anycasted. When the clients track the best performing servers, they generally tend to gravitate towards the Anycast servers because they're usually spread out across the network and thus topologically closer to the recursive resolvers. So they take the lion's share of the queries, and the unicast servers that are listed handle people who for some reason can't talk to the Anycast server or who are trying all of the servers, to collect that server data and see who performs the best. So it's absolutely possible to deploy both Anycast and unicast at the same time, and that may be advisable in many situations. Excuse me a moment while I resize my windows here so I can read the question. There's a question about zone transfers. It certainly would be possible to provide a unicast IP address for zone transfers. From our perspective, since there are multiple root servers that offer it, and there's also ways to get the zone directly from IANA, we don't see a need to do any additional engineering at this time to serve up the root zone. And in fact, generally speaking, the zone transfers work great. The only problem we've ever seen widespread is that a particular software distribution for a while listed F-Root as the only source of zone transfers and not the 3 other routes that could also provide it. And so when the users were configured to only go to that single server, we saw a very small amount of users reporting that they could not get the zone transfer. But considering the scale of F-Root and the number of queries we answer, we would get only perhaps a query every month or 2. So it's our belief that the failure rate of the zone transfers is extremely small. And here's a map for you of where F-Root is located around the world. We're always interested in filling in this map. We're particularly interested in putting new nodes where there is no F-Root node on this map, and even more so where there is no root server node at all, which is a different map. But if you happen to know of people in a country or area that has no root service, we'd love to talk to them about deploying F-Root there. So I'm going to summarize Anycast here in a moment. This is a great opportunity to ask any questions you have about our operational experience. Put them in the Q&A tab. So Anycast is a routing scheme that can be useful when deploying some applications. And again, I really want to stress the routing aspect of this. This is a case where the server admins and the network admins really have to work together to optimize the service. The configuration, for the most part, is in the network to set the metrics correctly and get the routes going where they need to go and make sure that there's no poorly configured load balancers or middle boxes. The server configuration looks pretty much like any other IP address. It just happens to be the same one on many different servers. There are some protocol level implications. I gave a high level overview. Obviously, if we wanted to do a deep dive into any one of those protocols, we could look at all sorts of scenarios for them. I wanted to give you a taste here of the things that you need to consider. But at the same time, I really want to impart from our operational experience that DNS in particular is very well suited to Anycast deployments. I think it's Anycasted by an awful lot of people that nobody knows are Anycasting it. Most people don't expect that their ISP is Anycasting their resolvers, yet an awful lot of them are. Many of the TLDs and major domains that you have out on the internet are Anycasted today, or at least served in part by Anycast servers. And so it's very popular, very often done. So don't be afraid about doing it. Deploy it inside of your network, deploy it across the network. Use a service like ISC's SNS to Anycast your domains for you so you don't have to do the work. It's always possible to outsource as well. And so I'm going to hand back to Johanna here for just a moment for a couple of quick things on our upcoming events, and then I will answer some more questions. So please continue to type your questions in the Q&A tab. I see a couple there, and I'll be reading them and preparing to respond to them.
Thank you, Leo, for that wonderful presentation. So just before we start our last Q&A session, I just wanted to mention a few things. So ISC, we have events and training sessions happening all over the world and also online. In terms of webinar, we have 3 coming up. We have the Anycast, another Anycast webinar, but that's in Spanish version next week. So if you know of anybody, you have colleagues or connection that you think may be interested in such a webinar, please let them know. Send them to that link, isc.org/webinars. We also have another webinar, Cybercrime, that's happening on the 22nd of May, and we have IPv6 on the 12th of June. And in terms of training, we have all those trainings happening, IPv6, DHCP, Intro to DNS and Bind. That's happening in Amsterdam and Virginia. We also welcome any suggestions if you want us to present a webinar on any particular topic or training on a particular topic. Please feel free to contact us and let us know. We would love to hear from you. As a token of our appreciation for attending this webinar, we're offering this special discount for training sessions. Following this webinar, you will receive a thank you email from us with a coupon code that you can use to claim this discount. And that's it for me. I am going to start taking in questions for Leo.
Awesome. While I'm answering questions, I'm going to throw up one more poll. ISC does not have a training course today on Anycast, and so I'm curious if anyone would be interested in attending an actual formal class on attending Anycast. So if you could answer that poll, it might help us decide whether or not that's worth developing or not. And while you're answering that, I'll get to some questions. The first question is, I assume it's possible to Anycast some of your NS entries and unicast others. Is this common? Absolutely. That's how the root zone is configured today. I forget the exact breakdown, but it's roughly half of the servers are Anycasted and half are unicasted. And it's very common to deploy that way. By having one unicast server, you can ensure clients have a host they can contact if any of the Anycast problems that we went through occur. And again, most DNS software, particularly Bind definitely does this, but several of the other packages do as well, they track the server response time and try to go back with queries to the server that responded the fastest. And so if you think about deploying, 1 or 2 unicast servers and then maybe 5, 10, 15, or 20 Anycast servers, the Anycast servers are generally going to be closer to the majority of the clients, and they're going to draw most of the queries as a result. So you actually sort of organically get the kind of load balancing that you would like to see across those services. So it works very well to deploy Anycast and unicast alongside of each other. Another question, have you ever seen Anycast deployed at a .edu? Absolutely. I would say many educational facilities have deployed Anycasted recursive resolvers for the exact same reasons that ISPs do. You know, you're providing service to students or whatever. Some boxes are going to have to be deployed with manually configured DNS entries. Not everything uses DHCP, and so Anycasting your resolvers is a great way to make that easy, to provide redundancy, to be able to scale the service. You know, if you need more capacity, you just toss another server at it. So I think a lot of EDUs have done the recursive resolver. The authoritative domains, I think it's a little less common at EDUs. Generally speaking, they have fairly stable campus networks and are serving local populations, so I think a lot of people see a little less need, but certainly some of them have Anycasted. And another option is to outsource to a service like ISC's SNS, which would Anycast your zones as well. But certainly both of those models would apply equally well in a EDU environment. Another question that I've got here is that someone's considering replacing some pairwise appliance-based load balancing of authoritative servers to provide greater reliability and lower latency. I think that would be an awesome thing to do. Again, DNS is so well suited to Anycast. If you were writing a protocol and designing it to be Anycasted, DNS is almost as close to perfect as you can get. There's a couple things you might change, but happenstance makes that work really well. And you know, most of the load balancing appliances, quite frankly, are just very heavyweight. They have a lot of features for load balancing web requests and other stuff that aren't needed for DNS. So they're complicated to manage, they're expensive, and it's easier to simply do Anycasting of the service than it is to use the load balancer. So I strongly recommend looking into it for your DNS services. Another question, is it useful to have more levels than local and global for Anycast, for instance, regional and continental? Certainly people have deployed that way. Again, you can use any routing trick at your disposal with an Anycast address. So if you look at some of the things people have done with BGP, they have communities that limit route propagation to particular regions or networks, and all of those things can be used with Anycast routes as well. And it sort of depends entirely on what service you're going to Anycast and what your user's expectations are and your expectations are for the service as to whether or not more levels make sense. Obviously, and this is a general comment that has nothing to do with Anycast, I find the simpler things are, the easier they are to manage. So I would encourage everyone not to overcomplicate this. But I can definitely think of some scenarios where having 2, 3, 4 levels, depending on what you're trying to do, could make sense. I also see the same person who asked about, or I think somebody different about the EDUs, was wondering if I could provide some contacts. I might be able to do that. If you want to send me an email so I can take this offline, I will send you my email address here in the chat in just a moment, and you can do that. And I'm not seeing any more questions at the moment. If anybody else has one, we've got just a couple of minutes left, so feel free to jump in there.
Leo, did you answer the one from Greg at the top about impact on using DNSSEC and Anycast?
Oh, up in the chat? Or no?
No, it's in the Q&A. I think it's the third question, the fourth question. But I don't recall you answering, or maybe you did and I missed it.
I don't think I'm seeing it in my Q&A. It looks like we got a little WebEx bug. Could you read it to me?
Sure. It's from Greg. It says, any impact when using DNSSEC and Anycast? And then the next question, it's from him as well. Don't Anycast server need a unique IP address as well for network management?
The second one's easy, yes. That was one of the small points I glossed over at the beginning of this, but generally speaking, you find that any Anycast box also needs a unicast IP address, so you can SSH to it, SNMP to it, any of those sorts of management functions. You'll want to run your probes to be sure that it has valid zone data to the unicast address so that you can monitor all of your boxes. because the alternative is you're only going to reach one of the Anycast servers you have deployed. So usually a unicast address is also required. Regarding DNSSEC, generally speaking, there are no issues with DNSSEC deployments that I'm aware of. You know, obviously your DNSSEC configuration needs to be proper and pass all of the usual things there, but there's nothing specific to Anycast that would impact DNSSEC.
Okay, good.
Aha, and WebEx is definitely being a little slow. Those questions just appeared, at least one of them just appeared in my QA tab.
Okay. Okay, we're at the end of the hour, and I do not see any more questions. So any last words from you, Leo?
No, I'd just like to thank everybody for attending and appreciate you taking the time.
Thank you, everyone. And this webinar will run one last time at 7 p.m. tonight, Pacific time. So if you know of anybody that can benefit from it, one of your colleagues maybe, please let them know. Thank you so much. Bye-bye.